Now, our second case for resisted motion is one where our resistance is up, motion's upward, the resistance is proportional to the square of the velocity. So what does that mean? Well, particle's moving upwards, but its resistance is going to be gravity, and then we've also got another resistance that's proportional to the square of the velocity. So that's what's acting against it. So mass times acceleration would equal minus mass times gravity minus mass times k times v squared. So the m's cancel, and we get acceleration must be minus g minus kv squared. So there's our starting point. And we want to do in part A here, the vertical displacement of x. So given to us in terms of velocity there. So we're relating x and v. So if we're going to relate x and v, well, let's go back to v dx. And that's minus g minus kv squared. So divide by v and then take the reciprocal, gives us dx on dv is equal to minus v on g plus kv squared, which is not too bad in integration because that's just going to be a log function because we've got a v there. All we really need is a 2k there, so that's where the minus 1 on 2k comes from. And we know that when t is equal to 0, x is equal to 0, and v is equal to u. So we're able to do those substitutions in. X is equal to 0, minus 1 on 2k, natural log of g plus ku squared plus the constant. And then we're able to get our constant there, 1 on 2k, natural log of g plus ku squared. And then our expression for x can look like that, which can be cleaned up to 1 on 2k, natural log of g plus the u squared over g plus v squared, plus we've got the negative there. So we've got our expressions there, and we've actually left out the k there, so we should have a k in there. So make sure we put that in. So the next one is we want to see that the maximum height is given by that expression. Well, again, we know when we get a maximum height, so x would be equal to h, but our velocity is 0 because it's actually stopping. So our x value we substitute h, our v we substitute 0, and we get the g plus ku squared on g, which again we can do a little bit of cleaning up because the g's can cancel, and that's where we get the ku squared on g there, and we've multiplied by the 2k on both sides. Our next part wants us to see the time taken t to reach its maximum height is given by this expression. Well, we need to do that. We need to get our expression for time in terms of v. So we go back to acceleration and we take v to t as minus g minus kv squared. Again, a little bit of manipulation. We can factorise a negative out and take a reciprocal, gives us 1 over g plus kv squared. So integrating both sides with respect to the variables. So we have our dv there. Integral of t will just give us t. Now, the way we're going to manipulate this one is we know that it starts at u, the velocity would be u, and then we're going to go to the point where we would get the velocity being 0 because that's where it reaches the maximum height. That's where our value of t comes in, because technically we've integrated the t between time 0 and time t. So that can be integrated, get t minus 0 gives us the t. So integrating this one and doing a little bit of manipulation, we get the minus 1 on k to v on g on k plus v squared gives us an inverse tan function. So we get the minus 1 on k there, 1 on square root of g k, and we get the inverse tan of square root of k on g times v. Between 0 and u, so we put 0 in, we put u in, and we get u on c. Now, we notice c here, we've started to use c squared is equal to g on k, so that's where that's starting to come into play, because c is equal to g on k, or c would be equal to the square root of g over k. So that's where that's all starting to come into play there. So if you wondered what happened to these, that's where the c is coming in, and that gives us the expression we want. 1 over kc inverse tan of u on c. So we could have integrated like we did before and get our constant integration and then play around with that. But this is just another way to do that, and it's a little bit more efficient as we go through. The last part here is now getting the velocity at time t to be given by that expression at any time t, where c squared is equal to g on that, on g on k. So we know that t would be equal to this expression, which we know integrates to minus 1 on kc inverse tan of v on c, plus the constant. And so we know when t was equal to 0, v was equal to u. So our constant would be 1 on kc inverse tan of u on c. So that gives us our expression there. If we multiply through by kc, gives us kct. And this is all now just manipulating to get v by itself. So this is where we've got to use our algebra to get from this expression to this expression. So multiplying through by kc, and then we take tan of both sides. So tan of this one be equal to inverse tan of that one. So when you look at that manipulation, we get the u on c minus v on c, or tan alpha minus tan beta, that's alpha and beta, plus over 1 plus alpha times beta. So, and it's starting to manipulate the algebra through. So have a look at the algebra that we get to clean it up to get down to uc minus vc on c squared plus uv. And then that means we could get this expression, c squared on tan of kct plus uv tan of kct equal to uc minus vc. Again, now we've got v by itself, we can factorise our v's out. So collect our terms, factorise our v's out, and then divide by the c plus u tan kct, because those expressions that didn't have v got moved across the other side, and that's where we get our expression for v. So have a look at that algebra that's involved there, and really once we've got our expression for t in terms of v, it's all algebra just to go and manipulate to get back to v, expression for v in terms of t.